So I'm just going to give you a brief overview about the patient health prediction work group, what we do, how you can get involved, and then we're going to have 5 exciting presentations that you're going to see about some of the research that has been coming out of this group. And you're also going to see, though, that we're actually doing a lot more research, and hopefully from viewing this, some of you will be joining our call. And we've got actually a work group call in 2 weeks' time. So hopefully you see some new faces in that call. So firstly, what is patient health prediction and what do we do in this work group? Is basically a set of us as researchers coming together and coming up with ideas of best practices for how we can develop patient health prediction models. So mostly prognostic models, but we can also do diagnostic as well, using the observational data that we have in the OHDSI network. So we use the OMOP CDM as our data format, and we do lots of different research. Some examples here. A lot of the research is actually on methods research questions. So this will be something like, what is the impact of your design for your studies? If you do a case control design for a prediction versus a cohort study design, how does that impact the model? And how does that impact things like external validation of the model across different data sets? If you have questions like that, come join our group. We run a lot of network studies, and you'll see in our best practice methods research questions, we tend to do network studies. And you're going to see this in the presentations that following my introduction. You're going to see that majority of these presentations are actually going to be using a network study. They've used multiple databases. And this is one of the key benefits of the OHDSI patient health prediction work group, is that we have a lot of databases in our network. So we can actually look at the impact of different design choices across lots of different databases. We can look at how well a model does, not just in one database, but across a broad set of databases. We also spend time developing prediction models. We take the knowledge that we gain from doing these methods research questions, we implement that as best practices, and we develop models. And you'll see that we've actually got a COVID prediction model where we predicted COVID severity during the pandemic. And you're going to see actually AX going to be presenting a follow-up where we're going to take that model and actually see how that does. How did that stand the test of time? And it would be interesting to see actually how well that did. We also have an R package that we actually have multiple R packages that lets us do the best practice research and the model development, the model validation. So we actually have a patient health prediction package, and then that does like logistic regressions, gradient boosted machines, like your standard kind of machine learning models. But we also have deep patient health prediction that AX been leading, and Henrik have been doing a lot of work, and Chung-Soo creating that package. And that's actually letting people now do deep learning, the advanced kind of deep learning methods very easily with any data mapped to the OMOP CDM. So if you want to do deep learning, there is a package that makes that very feasible for you in the OHDSI ecosystem. And we also just generally have a fun discussion. So it's just, we get together once a month in our meetings, and we have a discussion about lots of different prediction tasks. Whatever someone wants to talk about, we're always open to discuss in our work group meetings. We also have a team environment where you can chat and you can plan projects. And we also recommend that people, if they have a specific research question, they can create smaller groups that can meet more regularly to work on those projects. And you'll see a lot of the presentations that were done that are going to be presented have taken that structure where it's smaller groups from the bigger group that have a common interest that start working together to answer that. So you're going to hear from 5 different presentations. The PLP work group is very active. So this is all work that's being done by people within the work group. The first presentation is going to be from Hen, and he's going to be showing you his method that Tal and himself have developed to estimate external validation without sharing patient level data. So this is really important. When you have a model, you want to see, will it work? Will it work on different patients and different databases? And their method actually can give you insight into that without having to have the complexity of recreating that patient level data and figure out how you actually share that or use that. And then you're going to hear from Henrik. He's been implementing that deep patient level prediction package as a network study to compare deep learning, some very advanced methods against your logistic regression and your standard methods, and actually seeing how well that does for lots of different prediction tasks. And then Alexander is going to be presenting on a review that he did, which was investigating what makes models successful. So a lot of prediction models aren't implemented. They're developed, they're published, and that's where they stop. But there are some that are being implemented, and what is it about those models that are special? What is it that makes them implemented? So he's going to be giving some insight into that. And then you'll hear from Egill. So this is an earlier project, still in the development. So if you're interested in this, I'm sure he'll be happy to hear from you. And this is actually taking a model we've got and actually implementing it over time. And then finally, you'll hear from Ross, where he's actually going to be showing you some benchmark tasks that we're developing. So when you do best practice research, it's really good to have a kind of set list of prediction tasks that you can do your methods research on. This doesn't exist at the moment. No one really has these benchmark tasks. So we're hoping that by giving a set of benchmark tasks, we can actually make methods research more consistent and better. So these are some existing projects that are going to be expanded on in the continuation of this presentation. We also have a lot more work going on. So people in the group are doing federated learning. We're actually going to probably end up having another little side group that comes out from PLP that will be its own dedicated federated learning group, because there is a lot of interest in this area. We also have people working on more best practice research questions. So, for example, how does the choice of metric for hyperparameter selection impact the model? This is a question that I know that there's kind of ideas at the moment of how to actually create that kind of research question, the study, and actually run that. I know there's a lot of interest as well from the community of like the data, how that impacts the final prediction. I know, Claire, you have a lot of interest in kind of how the data quality and the type and the density would have consequences on the models. So this is something there's people have an interest. And then counterfactual prediction. So this is actually the type of prediction that could actually be used to help personalize medicine and show people this drug is better for you. So there's actually quite a lot of work going on in counterfactual prediction as well in the group. So there's a lot of topics, and it's kind of never ending. So if you have any topic of interest you want to discuss, come along to the work group, join the teams and start chatting, or come along to the weekly meeting, and we can actually discuss whichever topics of interest that the community have. How to get involved. So the first thing you want to do is you want to join the work group. There is a form. I put the link in here. So I'll share these slides and you can just click this link. But this will open up a form. On the form, you put in your details. You want to make sure that you tick the PLP patient health prediction. This will then give you access to the OHDSI teams for the patient health prediction, and it will also give you the invite for the monthly meeting. Next meeting is going to be on the 14th of August. We already have an exciting presentation planned for that meeting. And so I hope to see some of you, some new faces there. It's at 9 a.m. Eastern time, which is good for most people, but it's hard to find a time that obviously works for everyone in the world. But hopefully this is a convenient time for the majority of people in this meeting, especially as you're joining right now. So it probably isn't too late if it's not too late right now. And then if you're interested as well, you can always reach out to myself or Ross. And I've got my email on the last slide. So if you, on the last slide, you can snapshot my email and send me an email as well if you want to find out more about the group. Here, I just wanted to kind of stress that, or highlight that we have a lot of our packages. The kind of core package is the patient health prediction. It's pretty easy to install. You just run this one line of code to install from GitHub, and then you can use this to develop models from any data mapped in your own CDM. If you have data, you can actually connect to that and start developing real models. If you don't, you could use Eunomia, which is a synthetic data set that's available as another R package to test out the PLP package. I just wanted to show this really to show that it's consistently being maintained. This plot that I've got here is just showing you a by year number of commits. And you can see that this isn't changing. We are maintaining this package. We are changing this. We're taking feedback from people. So if you have any things you like or dislike about this package, come and tell us. If you want new functionalities, come and tell us. If you want to be involved, let us know, and you can start being one of the people that actually will commit and actually add to this plot. So this is just a package that will make prediction easy, but we're always up for feedback from the community and expanding this. And then as you're here, like we've actually got the deep patient health prediction package that Henrik is going to present on, and Egill's been working a lot on, that will actually do the deep learning, and it builds on top of this patient health prediction. So out of that, I'm just going to now hand you over to the 5 exciting presentations, and the first person to present will be Hen. So the floor is yours.
Thanks, Jenna. So this work was done with Jenna and with Tal, and Tal and I are both in the KI Research Institute in Israel. Next slide, please. So as Jenna already mentioned, when you train model on your internal data, and then you take them to external databases, often you see decrease in the performance of these models. That's the reason you need to external validate models to make sure they're actually working in environments other than yours. This task of external validation is often challenging, even with harmonized data as we often have. And in some cases, you have to do it iteratively when you want to find the best performing model. So 2 years ago, Tal and I published a paper that suggests a method to estimate external performance using just descriptive statistics, limited descriptive statistics of the external data. And the main the way that this method works is actually looking for patient-level weights that, once used in the internal data, actually induce statistics that are similar to the external data. And once you have this weights, you can compute performance metrics on your internal weighted cohort, and that would be your estimation of the external performance. And we say limited descriptive statistics would come from a specific effort to extract these statistics in the external data. It could come from the literature, from characterization studies. Next slide, please. So in this work, we set out to benchmark this approach on 5 different US databases. So in turn, we use each one of the databases as the internal resource, and the external, the remaining 4 as the external sources. We trained 4 model variants on 5 different outcomes. So all in all, we had hundreds of different external validations. For each one of these combinations, we extracted statistics in the external database, obtained the weights that induce the external statistics in the internal data, and then estimated the performance on the internal weighted data and compared it to the actual performance in the external data. Next. So this is just a subset of the results. Here we show just one internal database, Medicaid, and one outcome. And along the x-axis, we show the different external database, and the y-axis shows the performance, this case AUC. Different colors encode different model types. The filled diamonds are the internal performance, and the blank ones are the actual external performance. The axes are actually the estimations. One thing you can easily notice here is that the axes are pretty close to the blank diamonds. Next. Yeah, so this is just one internal database and one outcome, and we have results for all combinations of internal, external, outcome, and model variant. Next slide, please. Then we aggregated the results along for each one of the internal databases across the external databases, outcome, and model type, and show here 3 different performance metrics. The red, so these are the errors in these performance metrics. The red box plots are the estimation that we obtain using our algorithm, and the light blue ones are actually using the your best guess if you don't have estimation, which is the internal performance. And as you can see, the estimations are much better than the using the internal performance as your guess. And in vast majority of cases, the errors are pretty small. Last slide, please. Okay, so to conclude, we benchmark a method to estimate external performance using just statistics from the external data resources. The accuracy of this estimation depends on the diversity of the internal and external data, in the sense that your internal data have to cover the population in the external data, So in a sense, it's one-sided positivity in the causal inference sense. And you have to select the features you weight on such that your results would be accurate. And we have some recommendation and diagnostics in the paper how to do it correctly. We hope that this method will turn useful in pre-deployment assessments of models, and hopefully also expedite collaborations over model development. If you're interested in the method paper, the details and link are on the left side, and if you want to take a look at the code and perhaps use it, the GitHub repository link is on the right. Thank you.
Thanks, Hen, for this. This is really exciting work. I'm actually really excited to see. I think as well, we've had this issue in OHDSI where when we see a decrease in external validation, we never really know the cause. And I think this will actually potentially help us explain some of that as well. So I think there's lots of exciting work to come from this. So next person to present is Henrik. So Henrik, the floor is yours.
Yeah, I'll be presenting on a still ongoing but almost wrapped up study in which we compare the deep learning methods with what we call here conventional methods for prediction. So these are, for example, logistic regression and gradient boosting. And the background is that historically, learning methods, they haven't been doing so well on this rather sparse and really high dimensional observational data. And then as a result, the much simpler models such as logistic regression and gradient boosting, they achieved generally similar or maybe even better performance. And because they were much less complex, had much fewer parameters, they would then generally also be the first choice. And then recently there have been a couple of publications where, well, a couple new adaptations of deep learning models have become available. And in this study, we basically we set out to compare these new deep learning architectures or their adaptations to the conventional models. And this was also set up as an OHDSI network study. So I have here on the screen everybody involved that also supported the study. Next slide. We have a relatively traditional patient-level prediction approach for this. I guess the only exception is really that we are now also developing models on a GPU, so the deep learning models. So we define 3 outcomes: dementia, bipolar disorder, and lung cancer, which are taken from published clinical articles. We develop logistic regression, XGBoost, which is an implementation of gradient boosting, ResNet and transformer models on 6 databases, IPSI from the Netherlands, Awesome from South Korea, and Optum EHR and Optum SES are the Optum databases. So this is EHR and claims data from the US, and then data from Stanford and data from Columbia University. We internally validate these models, first of all, on a test set partition. We're looking at discrimination and calibration, and then also externally validate them. First of all, across the original development databases, but we decided to also add a couple more databases, which then also include the IBM claims databases, CCIE, MDCD, MDCR, and then also German and Japanese data. Next slide. This is basically what we get. We get an evaluation for each model, how it performs on each database. So you can see on the top, the columns are the 4 different prediction methods: ResNet, transformer, logistic regression, and XGBoost, and then also across the 3 health outcomes. And based on that, basically, we can now look whether these methods actually, whether there's any statistical difference in how they perform. So next slide. And what we do basically is we are testing for a statistical difference using the Friedman test. And if there is one, then we can actually use a post hoc test to rank the methods. And we do that in A first of all. So this is the first one for all the performance measures that we have. So internal and external validation measures. And there we see that it looks like conventional methods still do outperform the deep learning methods. But then what we also do is we look only internally. So only at the internal validation performance of the models. And there the Friedman test actually does not show any statistical significant difference between the methods. So as a result, we wouldn't continue with a post-hoc test. And then we also don't have this critical difference diagram for that. I'll go in a bit more detail in a bit about that. Looking then at B, that is only looking at external validation. And there again, conventional methods seem to outrank the deep learning methods. And then what we also did is we stratified by what we, well, more or less call large data and small data. So the Optum databases, Optum SES and Optum EHR, they were relatively large. And so that would be C. And there we again see that it seems like on large data, the difference on how the models, the methods perform is actually again smaller. So there's really only a significant difference between the two conventional methods, XGBoost and logistic regression, where logistic regression seems to be the worst ranking one. And then again, looking at D, this would only be small data. Again, the conventional methods outperform deep learning. And yeah, so I mentioned that there was no significant difference for the internally validated models. So then on the next slide, we looked a bit more in detail at that. So basically what we did is we created learning curves where we can look at the discrimination performance, in this case, AEROC, for increasingly larger subsets of the training data. And we can basically confirm that there's no significant difference by looking at, first of all, the dementia learning curves, where all the methods seem to converge at one point as long as enough data is available. If there isn't enough data, so that would be in the case of lung cancer or bipolar disorder, then generally the deep learning models, they don't achieve this plateau or don't perform as well as the conventional methods. And then also we saw that, for example, for the ResNet, we saw a lot of instability in training. You can see that, for example, on the bottom left, which most likely also with more data could be resolved. Yeah, so overall, probably conventional methods are still the way to go. And future work will now be, of course, looking into how we can improve the deep learning. Yeah.
Thanks, Henrik. This is, again, some really exciting work going on here. And I want to stress it's hard to do external validation of a logistic regression. To do the external validation at scale that you did for deep learning is really impressive. I'm not aware of any deep learning comparison that's taken this many databases. So this is really good. And I think this is an insight that agrees with what's currently being published, that the deep learning doesn't generally outperform, or the current deep learning, but it now sets like a benchmark that these are tasks that we can see. Is there a way of doing deep learning to outperform the gradient boosting or logistic regression? So I'm excited to see where this goes as well. So thanks. So next up is Alexander. Floor is yours.
Thank you, Jenna. Yeah, so we performed a systematic review on the implementation and updating of clinical prediction models. And this figure kind of depicts the pipeline and the current situation of prediction modeling. So a lot of models are being developed and internally validated, and then still a substantial percentage is externally validated, but then really few prediction models are being implemented. So if you could move on to the next slide. So basically, this systematic review aimed to look into the barriers and the enablers for implementation. And for that, we performed a risk of bias assessment with ProVast, and then also looked into tripod characteristics and the adherence of these models to the tripod characteristics. So first of all, the ProBAST assessment. As you can see, the majority of these models are assigned a high overall risk of bias. And I wanted to delve into the reasons for this, for ProBAST at least. So for the participant domain, the main culprit for assigning a high risk of bias is the use of observational health data. So according to the ProBAST authors in their explanation article, they advise ProBAST assessors to assign a model with a high risk of bias when observational health data is used. And then for the analysis domain, it's mostly assigned with a low number of events per predictor when models don't include a calibration plot. And then also when, for example, imputation is not performed for missing data. So in the systematic review, we try to identify why a lot of these models are being assigned a high risk of bias, and also advise researchers what to do when wanting to implement these models. So for example, if there's a high risk of bias, what should they do, etc. So if you could move on to the next slide. So this figure is kind of counterintuitive, but I'll explain it a bit so it becomes clearer to every one of you. What I wanted to depict here is that external validation is performed really infrequently, so only in 28% of the included models that have been implemented. And for your information, we included 57 models and 38 publications, so that puts it into perspective. And then of these models, 68% was assessed when it comes to impact, and only 12% of these models were updated. And then for model development and internal validation, only 21% of the models included a calibration plot. So one of the takeaways is definitely that the adherence to best practice, so for example, including a calibration plot, performing external validation, and having an updating strategy should increase. And apart from that, AI multidisciplinary teams should be established. A prospective registry would also aid in increasing adherence to best practice. And then concerning updating strategies, there's really limited research on what best practices would be. So that is also necessary to increase this. So yeah, that's what I wanted to discuss.
Thanks, Alexander. This again is really fascinating. I think we've seen a lot that the very few models make it to implementation. So I think just seeing what is it about the models that have actually been implemented is really interesting. And the fact that implemented models still have such a high risk of bias is kind of, that was kind of an alert to me that it's interesting. But I guess any model we developed, we're using observational data, so it would be high risk of bias. So I think addressing that and looking at other reasons and whether we can kind of maybe get observational data trusted more would be really good. And then I think as well, what you found here about lack of calibration and lack of updating strategy is key as well, because if you have a model, it's going to link up actually to what AX is presenting, but chances are you're going to have some updating strategy, because chances are things are going to deteriorate over time. So it's fascinating that very few models that are being implemented actually mention any updating strategy. So this is really key for kind of work that we need to continue as a group to actually get best practices for. So thank you. Next up is Egill. The floor is yours.
Thank you, Jenna. So this project is actually quite different from the other projects presented here, because this is work that's just starting. So I don't know how many of you remember, but in the beginning of the COVID pandemic, the OHDSI community came together, and this was slightly before my time, but you developed a prediction model for COVID risk. And it was very early in the pandemic, so the strategy used was to use a disease proxy. So the model was developed on influenza data and then validate it on COVID data, and actually performed pretty well. But now, when the pandemic is over, we want to do like a follow-up study. So what we want to do is now we want to take the original C-cover model and possibly like a different version that's trained on COVID data, and we want to investigate its performance during the pandemic. Next slide, please. So what we want to do is essentially throughout the pandemic, we want to validate the model every fixed number of months, and that depends a bit on how much outcome data we have. And we want to analyze how the model performance is affected by different events. So this is kind of the extreme case, like a pandemic, because there are so many things changing. So you have, like in the pandemic, we had the different strains coming up and like rising to prominence and being then overtaken by another strain. You had the start of vaccinations, which were rolled out in like different geographic areas at different times, possibly. So we want to see how well is a model developed at the start of the pandemic, how robust it is to all these changes. And then we want to also evaluate how, like in the beginning, when you have very little data from the pandemic, how does this strategy of using a disease proxy compare to just waiting a little bit for until you have more data? Like how does it affect the performance down the line? And then finally, we also want to look at, like Alexander mentioned, model updating strategies. So how will different model updating strategies affect the performance throughout the pandemic? Next slide, please. So this is just starting. So we have a repo. We are working on the study package, and if you want to get involved or have any ideas, like feel free to be in touch. Here, my email is on the screen, and you can also just make an issue on the GitHub issue. And the plan is to run this, well, first on the database, I think Clinformatics, the Optum claims data that the C-cover was developed on, just to make sure everything's working as it should, and like replicate the findings of the original studies. And then we want to expand it to more databases, and then finally run it as a network study. So watch this space, because we will be advertising this as a network study at some point, and we will also reach out to the original data partners and invite them to join. So yeah, thank you for your attention, and I put the ball back to Jenna.
Thanks, Egill. I'm really excited for this project. I really want to see how the model did. And I know we got a lot of negative kind of review comments because we used a proxy. So it would be really fascinating to see, like, had we not used the proxy of flu, if we had actually used COVID, could we have actually done better? And I think that will actually, it's just going to be a lot to learn. Hopefully we won't have this pandemic situation again, hopefully for our lifetime, but it's good to have the kind of knowledge of what to do in that situation if it does ever happen. So thank you. Next is the benchmark task, and I'll hand over to Ross for this.
Yeah, thanks so much, Jenna. So I'm going to talk, so I'll be the last person talking today, so talk a little bit about the benchmark tasks. And so this came about because we were doing a lot of methods research within the group, and then one thing we realized was that when we were doing this methods research, we were doing it on, a few problems. And actually, if you look within the field, I say problems, I mean like prediction tasks, so a clinical prediction task, so target, outcome, time at risk. And one of the things we realize is that, we're trying to compare these methods, we're trying to say which one works better, which one's more efficient. And yet each time you're seeing it run against a different set of clinical problems. And what we would like to do is to more directly compare these tasks. So the benchmark task come about is to say, hey, we're going to have a standard set of tasks that whenever you run a new algorithm, or you want to see how something impacts your your data collection, or maybe you're saying, hey, maybe even a pet project, you're going to say, hey, we normally throw away the least occurring 1% of data. What if that's 0.1% or 10% of data? anytime you make these decisions, you then have a set of these clinical tasks that are available to you. You can run it, and then you will know, oh, well, it's benchmarked. So we're going to say we're going to run, as part of this study, a benchmark of the tasks and say we've done it against these clinical problems in these databases, and these are the performances that we saw. So then when, you know, Egill and Henrik come along and they want to introduce a deep learning model, they can run it against these benchmark tasks, and they already have something with which they can compare against. So one of the requirements we had for this is we wanted them to be clinically useful. So we thought, well, you know, if we're going to spend all this time and energy making these models, then we may as well make models that we think are going to be relevant. The other one is we wanted them to be diverse, and this has a couple of interpretations here. So we wanted it to be on different disease areas. So we have, you know, cardiovascular disease areas. We have we've got like an ophthalmological disease area, and we also wanted to be diverse in terms of the size of the populations that we'd be looking at. So we're going to look at things that have, you know, lots and lots of population, lots and lots of patients in, and we're going to have a look at rarer diseases. So, for instance, one of the prediction tasks we're using is the COVID task that we developed a few years ago, and it's just about to be updated in the work of Egill, which has unfortunately, you know, lots and lots of patients available for it. And then another one is looking at a couple of surgical outcomes following a major non-cardiac surgery, which has quite a bit fewer, although still quite a few. And the idea is that we will continue to add to these tasks and say, you know, we really wanted to start developing models for rare diseases, and then we will have a set of tasks where we've said, hey, we've developed these models already, we've seen how it performs in rare diseases, this tends to be the approach that we should take. And then lastly, it has to be feasible and observational data, because we want to run everything against the OMOP CDM. Next slide, please, Jenna. So how did we do it? Yeah, so I think this was a really nice piece of work, which is that we actually crowdsourced this. So Jenna and I were discussing this project. I think we discussed this as a working group. And although we think we're all right at our jobs, we realized, you know, within the OHDSI community, we have experts in pretty much every area of epidemiology, diseases, and healthcare. And so we thought, well, why don't we use some of this and say, we want to come up with a set of prediction tasks that are relevant, and the best people we can ask that to is the people that would be using these tasks. So we reached out to the different work groups, and we asked them, you know, what task would you find useful? We also, at the OHDSI EU Symposium, not this year, but the year before, we had a work group where what we actually said, we tricked them a little bit. So we said that we would teach them how to run PLP, and actually what we did was we taught them how to run PLP, but then they had to come up with some interesting questions they wanted answers, and then we used that to then create the benchmarking models. And then lastly, we went through all the models that we developed over the last sort of 5 years, and we said, which ones of these do we think are really good and which ones do we want to grab? And we grabbed a few of those, and we put those into the benchmark tasks. Currently, they're available at the link. So I think Jenna will share the slides, or you can find this going through from the OHDSI GitHub. Yeah, at the moment, so we're refining the phenotypes. We've run some models initially, and we're hoping to get a first draft of this paper written in the next month or so. It's looking pretty promising. What was nice about this is that, unlike when you're normally developing a model, you're not worried about getting poor performance. What I was worried about is not getting a spread of performance. And what we've seen is, yeah, we're getting actually a really nice spread of performance for the different clinical tasks, which is then coming back to this idea of diversity at the beginning, where, you know, we don't want to only have clinical tasks that always perform well or always perform badly. We want to have a nice spread, so you can then just say something about the full range of your performance. Next slide, please, Jenna. Yeah, so the next steps. So we want to evaluate this across a network. So we've got some of these models developed already, and we want to start externally validating them. We think this will then give us a bit more information of saying, not only, you know, do we know how to develop the best models, we can then say, oh, actually, we know how well models developed in this way tend to transport. So let's say you're developing a model in a claims database and you want to use it in an EHR system. Well, maybe what we hope that you'll be able to do is to have some best practice guidance on what modeling procedure should I use in order to do this, to give my model the best chance of being, you know, clinically valuable and clinically implementable. We're also going to write a journal paper, so everyone that's contributed one of these tasks or helped with this is welcome to be a co-author on that. We also have regular discussions on this at the working group meeting. So if you're interested, you can turn up and we can have a chat about this. And then what we hope as well is that for people that are doing the prediction research in the future, they will grab these and think, hey, this is, you know, it solves that it solves a little bit of a challenge, which is, hey, what am I going to run my tasks on? What am I going to run my new algorithm on? And you just go, oh, brilliant, I've already got them. The infrastructure is already set up. You just have to plug your new method in. And what we hope is that, yeah, so the importance is just getting better and more comparable evidence for the different performances. So do you want to go to the next slide, Jenna? Yeah, so I think we have a couple of minutes for questions. I think we can do this about any of the topics. So if anyone has a burning question, then please speak up.
I'll throw it out to the entire group. One of the things I find really impressive about all your work is how you're doing such foundational work to basically prove how we can make prediction reliable. Maybe Alexander, I'll start with you, but I'm interested in everybody's perspective. But like, given the current state of best practices just outright not being applied or very rarely being applied, should we be ignoring all prediction models that are in current clinical practice? Should we be actively trying to discourage their use? Or do we need to basically kind of like reset and start building new models that are actually following practices?
Is this a question for me?
You can start.
Okay, all of us. Okay. I mean, I think the models that have been implemented should definitely still be used, but with a side note. So for example, if models have a high risk of bias according to ProBAST, I think that doesn't necessarily mean that these models should not be used anymore. But I do think that other measures should be taken to kind of prove that maybe a high risk of bias in ProBAST doesn't mean that they would not be reliable in practice. So for example, a good impact assessment and then also an external validation could definitely make this clearer to the user in the end.
Evan, go ahead.
Well, actually, I want to wait and see if Jenna or anybody else wants to, or Ross want to chime in on that question, because I think there's a lot to unpack there. And then I have another question if there's time, but I'll leave it there.
Yeah, I think maybe I can jump in on this. Jenna, you want to say something? So I think this question of best practices and modeling procedure and then implemented models are sort of two slightly separate things. So we have an idea of what some best practices are for developing a model. But I think, for instance, Alex touched on this here, which is so the ProBAST statement suggests models developed by observational data are going to be at a high risk of bias. But something being at a high risk of bias does not mean that it's at bias. So sometimes I think of this like, if I ask you whether I should buy a lottery ticket, you would say no because you're not going to win. But if next week I've won the lottery and then I say, should I have bought this lottery ticket? It would be pretty silly of you to say, no, you shouldn't have done that. And so I think we see that, so like a model would be called, it's at a high risk of bias, but what we actually really need is something actionable based upon this, which is, well, how do I show that it is biased and what direction that bias is, and then how can I fix that? So I think there's these questions of, how do we develop models that give us the best chance of a successful implementation? And that's what we would talk about with like PLP best practices. And then I think there's the other question, which is, how can we show that when we've implemented these models, they're safe and they benefit patients and they've given some sort of, either a financial benefit or time-saving benefit, or they've improved treatment. And that's, we have to do things like implementation studies for that. And what I would like to see is that we see some of these implementation studies. This is what Alex has picked up in his review really nicely. And we can try and learn from that and say, okay, so, we saw these models were at high risk of bias, but they've been implemented and they work. So therefore, that should be able to tell us, we can go back and we can inform our best practices around this. So I think Patrick asked quite a pointed question. No, I think we should not immediately withdraw all these models from practice, but I do think we should learn from where we see a disagreement between, a well-implemented model and best practices, and try to figure out where that's going wrong and how we can improve on that.
Very good. Evan, and then Kong.
It's I guess it's similar to the just on the heels of Ross's comment there. I was curious as to what some of the people who are doing this research think about that PROBAS statement? It strikes me as kind of quite analogous to saying, well, we can't really learn anything unless we do a randomized clinical trial. So to kind of state outright that everything that has its origin of observational data would serve to greatly restrict the models that we'll ever create. And so I'm curious as to how you think you go about changing the hearts and minds within that broader, I guess, community that might be coming up with these tools for assessing bias. And that's a big part of your work. But if there's if you had to kind of come up with a 3-point plan, what would it be to try to start to convince people that using observational data can be a fruitful way of creating and scaling up prediction at the bedside?
Yeah, maybe I could say point 1, but I think we need to take the same approach that Martin Schwemi took with the LEGEND study. And I think, you showed the comparison of these are drugs that have a clinical trial and these are drugs that we've compared. And I know that the 2 circles and one is just like completely filled in. And it's even if, and I'm not sure, I believe that the evidence is of a slightly lower quality, even if it is, at least there's some evidence. Whereas at the moment, we're treating a bunch of patients who wouldn't fit a clinical trial inclusion criteria anyway. And I think we can take a similar approach to that.
Yeah, I think that one of the reasons that there's this lack of trust of observational data for prediction is probably because there aren't that many implemented models that have come from observational data. But I think as we start to kind of get the framework more developed to actually implement models that come from observational data, and I think that's going to expand. Like people are developing a lot of models from observational data, and people are making it easier to implement and be used. I think then we can start doing assessments and actually expand the PROBAS to actually say, okay, maybe if you do X, Y, Z with observational data, you get good models still. So I think it's just really just more research into when does observational data lead to good models and when does it lead to bad models. And I don't think we should rule out observational data for prediction, but I think the problem is there's just not enough evidence right now that it gives you trustworthy models. But I think we can do research to get there.